Participated in our TechNation Wednesday webinar series. We have had over 180 pre-registered attendees for today's webinar, and we are thrilled with the tremendous turnout for the presentation. We are proud to offer these free webinars as a way to educate and provide valuable information to the healthcare technology industry. We will offer 1 or 2 of these webinars every month on Wednesdays, focusing on issues pertinent to the biomed, clinical engineering, and imaging service community. We always schedule the most sought-after and dynamic speakers in the profession. We'd like to mention that many of these same speakers and presentations are held at our biannual MD Expo, and our next expo will be the inaugural MD Imaging Expo, July 16th and 17th in Indianapolis. Please visit mdexposhow.com for the entire educational schedule. Our next webinar in April will be Wednesday, April 30th, and will be a 4-person panel discussion on what's new in test equipment, featuring representatives from Pronk Technologies, Fluke Biomedical, Daytrans Systems, and BC Group. You don't want to miss that one. A few notes before we begin. Your participation today makes you eligible for 1.5 CE credits. An email survey about today's presentation will appear on your screen immediately following today's closing remarks. Once the survey is complete, we will email you your certificate with the CE credits within 2 weeks. In today's webinar, all lines will be muted, but you can submit questions during the presentation by using the questions feature on the dashboard on the right-hand side of the screen. If you're having any difficulty, please email us at webinar@mdpublishing.com. That's webinar@mdpublishing.com. We would like to thank today's sponsor, Axess Ultrasound. Axess Ultrasound team provides high-quality ultrasound service, repair, training, and parts to over 900 healthcare facilities worldwide. Please visit www.axessultrasound.com for more information. Last but not least, our presenter today is Bob Broschart, Director of Technical Services at Axess Ultrasound. Bob will present ultrasound probe technology for the 21st century. He obtained a BS in Electrical Engineering Technology and a certificate in Ultrasound Physics and Technology. He has over 30 years experience in medical equipment manufacturing, engineering, service, and sales management, and has instructed product classes in ultrasound for OEMs and ISOs, both domestically and internationally. Okay, without further ado, Bob, take it away.
Thank you, sir. I appreciate it. First of all, I want to thank everyone for attending and for TechNation giving us the opportunity today to hopefully provide some insight on, in this case, ultrasound probes and what that means to you now and in the future. So once again, I want to thank everyone for attending. Title of today's talk is, as you can see, is Ultrasound Probe Technology in the 21st Century. And like many things, I know when I was a kid, we thought by the 21st century we'd all be in spaceships, but we're not there yet. But ultrasound probes have certainly migrated in the last 10 years to something that we didn't see in the beginning of this industry. So kind of just a brief outline of what we're going to go over today. We're going to talk a little bit about what probes are like today, the technologies and so on that are currently out there, you know, kind of how that technology has even changed and how things are continuing to change. We're going to go through some of the materials, talk specifically about single crystal arrays, and again, just how the probe technology is changing there. A new technology that's been in development for just a few years, SEMA technology. We'll touch on that. We're going to talk about those of you that are in ultrasound and have dealt with probe problems. You're going to know what I mean by dead elements, so we're going to talk about that. Kind of defining major and minor repairs and what those really consist of and what they mean to you. Why it is we do what we do in regards to probes and probe repair and probe problem identification, why it's important. Lastly, kind of what this means for you, what these new technologies are going to mean for you on a day-to-day basis. And then at the end, we'll have a wrap-up Q&A. At any time, as John had said, you can ask a question, and those will get pushed to me, so I'll be happy to answer those as we go through the presentation. So just talking a little bit about probes, again, of today and yesterday. As you can see, the picture on the right is actually from 1954 and was the world's first actual ultrasound imager, if you will. And you can see we've progressed from where the patient or subject in this matter had to sit in more or less a bathtub with this huge device beside him in order to generate an image, to now we have the portable systems and even handheld systems. And you may or may not know, Siemens has one of the first wireless probe handheld systems out on the market as well. So there's been a dramatic change, obviously, in the system side, and as we'll go through this, you'll find that probe technology is driving a lot of that actually on the system side. Now today, and this is just getting into some materials, kind of give you a baseline of what probes are, how they're built and what they're made of today. Most ultrasound transducers today use a composite material, commonly called PZT. They're ceramic crystal arrays. One of the reasons that most manufacturers use those currently, they are easy to produce, very repeatable from a manufacturing perspective, little waste. They're very good at making them, the array companies, as well as the ultrasound OEMs themselves. Relatively cheap, speaking, relative as always, and they have a very well-established performance level. So there's not a lot of issues with acoustic power and so on. It's kind of the manufacturers know what they're going to get out of these arrays. PZT arrays are used in all probes. As you can see, curved, linear, convex, transesophageal probes as well. And every manufacturer on the planet uses them. PZT arrays are actually an enhancement from some of the older annular and ring arrays of 20 years ago. One of the things on PZT arrays, ceramic arrays, is that they do have a limited amount of elements. They go typically from 64 elements, which you'll find in most transesophageal probes, to up to 288 probes in some of the multiplexed linear probes. But so there is a limit as to how many elements they can actually have with this type of probe technology. Now, some of the element characteristics of PZT, it is a piezoelectric element, so you know, it's subject to being hit with an electrical pulse and has a natural piezoelectric property to it. It emits the sound and send and receive through the same element. Again, it's a natural material, quartz, tourmaline, and essentially salt. There are some man-made ceramic materials that they add, lead zirconite titanate for PZT, and then barium titanate in what's called a PVF material, which is a similar composite array. Now, one of the things about PVF arrays is they've been developed to kind of match the acoustic impedance of the body, the human body, and closer to that of the soft tissue. So obviously, from a sound perspective, if the impedance of the probe is closer to the impedance that your body naturally produces, basically the better image quality you're going to get, the less signal loss and so on. The only problem with PVF, and I've got a little picture here to show you down in the corner here, in PVF, those materials are not naturally piezoelectric. So you have to use a process called poling, and I'll get into poling a little bit later, but it just gives you an example. It's a process that the manufacturers of the array have to go through in order to turn those crystal arrays into a natural piezoelectric property so that they can transmit and receive ultrasound. Now, this is just a little diagram kind of showing you a very, very rough outline of how current composite PZT arrays are made. Basically, the manufacturers put in a powder. It's crushed raw earth crystal, and they form these actual arrays. I've seen this. I've been to several array manufacturing facilities, both with OEMs and independent array manufacturers. They're huge ovens. They heat these things up to several thousand degrees Fahrenheit, and then they create these blocks. Then once they form the crystal, then it goes over, and this is obviously blown up dramatically, but these are individual elements. So they have to do an alignment on these and form these. Then they're usually put into a resin or epoxy block to hold the individual elements together. But again, it just gives you, kind of a ballpark view of how these arrays are put together. Again, one of the things that are used nowadays in the PZT arrays is called dicing. And essentially they go through with a very, very fine, for lack of a better word, bandsaw, or not bandsaw, excuse me, circular saw. And they actually cut these arrays. They fill them in with either a polymer or some type of epoxy material. And they do what's called a dicing process. And they have to put a spine back here along this edge, which actually holds the arrays, or the elements, excuse me, together. And then that forms what we call the array stack, or what you would see in the probe is the actual array itself with the lens. And again, this shows some of the fine pitch dicing. From a manufacturing standpoint, it's a 1:3 composite type of array. Just to show you this small size of what they're doing, and this is an outline of what a diced array looks like in a composite array. You can see that the groove width is only 0.025 millimeters. So it's very, very, very small. If you saw these saws, I can't even describe to you how tiny they are and what they look like. So you have a very small, you have a grid pattern that you cut in here for your dicing. And again, I mentioned the array stack a moment ago. This is kind of a pictorial of what that array looks like. So this is kind of from the back side here. Every transducer array has to have a backing layer. The backing layer is used to absorb sound that scatters, so that sound is not passed right through the array, and you lose your actual focusing of the beam. Here's your elements through here. This matching layer, that has to do with the acoustic impedance. Every array's got some sort of matching layer in it. And then this is the acoustic lens piece right here. This is the piece that you normally see on the outside of the probe. It's generally a rubber silicone type of material, and that's the part that obviously touches the patient. All probes have some sort of RF shielding, again, to keep down on RF noise, and then obviously you have your outer case, which can be a plastic or in some cases a light metal housing. Now, a little bit earlier, I talked a little bit about polling. Excuse me, and this is an example and some technology behind what polling means. One of the things that happens is, excuse me, with the material, it's all the elements are kind of scattered. They all have a positive and negative pole to them, hence the word polling. So what you have to do, what the array manufacturers have to do, is after they've made that array, the crystal itself, then they have to orient it in the right position, obviously, so that it can be used as needed and correctly. So what happens is, this is a figure 1 here. It kind of shows you a picture of, this would be the array element coming out, forming and so on. And essentially what happens is, in order to poll these properly, they have to use a high voltage, high powered electrical current to the element, and then they also have to add heat to that. Now, they have to be very careful that they don't overdo it, because too much heat, too much power can crack that element And as you'll see later as we talk about dead elements, that's something that they don't want to do, especially in the manufacturing process. So figure 2 here shows a properly aligned array, PZT array, that's poled at the correct levels. Figure 3 shows you one that this would be representative of a PZT array that has come unpoled. And as you can see, some of the elements are starting to get out of alignment, excuse me. And that can happen, and I'll talk later in the presentation about that, through extreme heat, electrical power that's out of spec to the probe, and so on. So there are issues where arrays can just become depoled, when in fact the array is good, but you have to be able to repole it back into position like figure 2. Now here's an example showing a infrared view of a probe that has become depoled down here where the arrow is right here. Now this red here, this is electronics in the probe, that's okay, but this should not be this hot. Typically there should be some heat. Obviously ultrasound puts out some heat, but as you can see, this bright red, this probe is depoling because there's too much heat being generated by the probe in some fashion or form here. So again, it could be just the environment that it's in is too hot, something with the transmit power applied to the probe, etc. But this is not a good thing right here. Now that kind of gives you a baseline of again, where most probes are today. As I said, almost all probes out there in the past 10 years or so have been in this composite PZT type of array. But as things change and equipment manufacturers have developed newer applications, for instance, for ultrasound, as many of you know, ultrasound is now used in musculoskeletal imaging for tendons and ligaments and so on in the shoulder, knees, etc. Podiatrists are using them in the feet. Just so many different applications. And that has required a dramatic change in image quality. And to get there, obviously probe technology has had to change dramatically. And some of that has then allowed ultrasound to move into markets that, beforehand we would have never thought possible with ultrasound. And frankly, musculoskeletal is one of those that several years ago you would not have thought you could use ultrasound to look at a shoulder. So some of the new technologies that have really come to the forefront, and probably the most popular one, is what we call single crystal array. And I'll explain what these are, but it's just PMN, PT, and PZN, PT, single crystal materials. And one of the things that, if you remember from previous slides, the PZT arrays are typically individual elements. Again, up 64 to 288 elements, and each one of those elements is connected via wire through the probe head, in through the probe cable to the system end connector. And it's got a send-receive signal on each element. Single crystal arrays are truly that. It's an absolute single piece. Think of it as a single piece of glass, crystal material, that's all one. And essentially the entire array is firing. And again, I'll get into this a little bit more, but there's a lot of electronic control over single crystal arrays and so on. But it is what it means, is a single crystal versus individual elements. Now, one of the things that single crystal does is it is absolutely, and I am a firm believer, and I've seen many images with various manufacturers' probes, there's a dramatic improvement in image quality. The performance is very, very good with single crystal materials. Element counts, even though, as I said, they're not individual elements, they are diced in a matrix grid, as you can see down here in the lower right, but this is all one piece of array material, crystal material. But what it does theoretically is it allows you to have from 1,000 to upwards of 9,000 elements if you were looking at it as a individual element type of probe. Does allow for something that some of the manufacturers, especially Philips, is using as called matrix array development. Some of the downsides to single crystals, and this is where it's going to affect you and your customers on a day-to-day basis. They are high cost to manufacture. There's a high failure rate even in the manufacturing process. So the yield that an OEM gets out of single crystal probes is a lot less than they do out of standard composites. So obviously that cost gets passed on to all of us. One of the other things is that there's very, very few companies out there that have really mastered the production and manufacturing of single crystal arrays. If you think of a curved abdominal probe, again, think of it in terms of this is a single piece of glass crystal material, and that manufacturer of the array has to bend that in that single piece, and has to bend that around all the matching layer and backing layer and so on, and it's very difficult to do that. And there's just a few companies that have really mastered that. So again, your supply side is very limited. They are prone to a bit higher failure rate because they're very, very sensitive to temperature changes. If they get very hot or very cold, they will fail. They'll break. And with single crystal, if the array cracks, then you're certainly dead for sure. The only thing I can say is that the last bullet point here, I see this as definitely the future of ultrasound probes and specifically array manufacturing. Again, if you look up here with the number of elements that can be generated and so on, the image quality, it's such that the manufacturers are really keen to develop more and more single crystal probes. Again, and we can just buzz through this, but this just gives you an idea of what this is a microscope look, high magnified look at what PMN and PZN are. They're both a niobate lead titanate is what it's called. One has magnesium in it, the other is zinc. And again, just kind of how these single crystals are made and some things showing a little bit, especially this picture, but they take in the raw crystal material. These are the ovens. These are the finished ones. But I think this is a very good illustration. This actually comes from Philips. This one on the left is your a magnified look at a standard PZT ceramic composite array. And here's a PMN single crystal array. So you can certainly see the differences in just the physical way it looks. And as I said on the previous slides, its performance is just dramatically different. This again is a picture from Philips. This just kind of shows the matrix layout. Again, what they do with single crystals is everything is cut into a grid pattern. In this case, they're talking 3,000 to 6,000 elements on this particular model. The picture here on the right I think is very interesting. That is a magnified human hair, and it's actually thicker, if you can look at that, if you're seeing it well enough, than the actual matrix grid cuts with the fine dice saw. So you can see that it's just minute as possible. But All these are cut into these grid patterns, and I'll get into that in a minute, and kind of how those are fired and controlled. Now, one of the one of the most complex probes out there right now, from a technology standpoint, is the Philips X7-2T 3D transesophageal probe. And this is just a diagram kind of showing a little bit of how that is made and some of the differences in it. As you can see, here's your array. This is your single crystal cut into the matrix. One of the things Philips does with this particular probe model is there's an ASIC chip that's actually embedded in here, pardon me, with the array. And that is programmed at the factory, and that actually controls the send-receive signals and other parameters of the probe, and it is unique to each probe and array. First one of its kind that I've ever seen. So it's all embedded here. You can see the size is very small, 1.5 to 2 centimeters, 1.2 centimeters in width. Cabling comes in here, and again, this is your array. It uses a very advanced electronic controls to actually control the sequence, firing and receive sequences. Again, just showing a matrix array. This one you can kind of see a grid pattern in the aperture. Again, this is just an example. If you were looking, you could actually see the ultrasound beams coming out. You would see them coming out in this grid pattern. And again, everything's centered around this array matrix pattern. Now this gives you a little bit of an example, excuse me, of some of the electronic controlling, and this is by no means totally comprehensive, but here's your transmit receive switches, and these are all multiplex, so they're all timed out, and this is what controls those matrix single crystal arrays and allows the system, with its knowledge, to control the sequence of send-receive so that you can get that image quality improvements by the way it fires and receives the ultrasound beam. Now, one of the new technologies that's been out there, and I would say it was started probably 10 years ago, maybe even a bit longer. It's something that's not commercially available yet. I do remember when it came out, it was going to be the next greatest thing in ultrasound, but I think they've run into some issues with it. But that is called CMUT technology. CMUT stands for Capacitive Micro-Machined Ultrasonic Transducers. Now, as we've talked before, composite arrays, single crystal arrays are all a crystal material, raw earth material that's converted into a crystal and fired to get a piezoelectric effect to generate ultrasound by vibrating that crystal. CMUT is the first technology that it's not using a crystal material at all. What it's doing is really using a component. They use basically a CMOS chip that they manufacture, and what they do is they put it using a micro machining technique here. They put a thin layer, almost like a membrane, on the top of a cavity. They cut a small cavity, and this picture shows a little bit. It's not as good. Again, here it acts kind of as a membrane on this CMOS chip, and basically what they do is using electronics. They apply that to the CMOS, and it makes it vibrate, and it generates what essentially is an ultrasound wave. If they, excuse me, they use a capacitance methodology to actually transmit the energy. It's very unique, and again, as I said, several years ago, all the manufacturers started looking at this because it's cheaper to make. And let me just go to the next slide here. Yeah, here we go. This gives you a little bit better look at that. Again, it's much cheaper to make. And I'll digress one point to give you an idea of the cost for the array manufacturers to manufacture the actual arrays. A few years ago, 5, 6, 7 years ago, maybe a bit more, the raw earth material that an array manufacturer or crystal manufacturer would purchase cost about $400,000 a cubic ton. They could get it. The primary suppliers then were China, Canada, and the U.S. Now, just through changes in law and so on here in the U.S. doesn't produce as much, and the primary suppliers now are China and Canada. And because of that, the prices now average for a cubic ton of raw earth about $1.2 million. So that's obviously driven the price up of everything. So that end result, once we get an ultrasound probe on a machine, that's part of the reason the cost is so high, is that raw material comes up. So again, the cost to manufacture those is all passed through, and the array manufacturers have to bear that cost as well. But when you're talking about making essentially a CMOS chip, and any of you that deal with components know that for the most part components are very inexpensive. And that is what is so attractive about CMUT technology, is that it's very easy to produce, very cheap to produce. Again, it's going to be highly electronically controlled. There is a multiplexer here on all CMUT probes. You can see here, and I just don't know, is it the future of ultrasound arrays? Right now, one of the problems with CMUT, and I think it's been one of the holdups, is they're having a lot of trouble getting proper Doppler signals, pulse Doppler signals using CMUT technology. You know, they can do color, but that's got some problems too because it's still the Doppler effect. So it's still out there. There's a lot of research facilities working on it. There's companies working on it, but where it's going to go, I'm not sure. Now here's an example. On the left is a standard ceramic PZT transducer looking at a carotid artery and thyroid. And to the right, you can see a CMUT transducer looking at the same vessel. You can tell there's not a huge difference in the image quality. Because CMUT is all electronic, what you're going to see, and you can see this picture I know is not great, but if you look closely, right here you can see some intimal lining, which is the inner lining of the carotid. You don't see it quite as well here, a little bit there, but not so much on this anterior wall. And if you look up in here through along the skin line, there's a lot of averaging has to go on in CMUT. The machine has to average the signals a lot more so than in a PZT array, for example. But overall, it's not a great difference. It's just going to give you a smoother looking image. So I know I've spoken to some people, and they're on the clinical side, and they're a little concerned that they might lose some detail with this type of technology. And here's another example, and this one's a little bit closer. As I mentioned here, it's just a little bit softer type of image. This one's got a little better detail on this intimal lining right here. But again, where CMUT's going to go, I just don't know. It would be interesting to see if they can correct some of the technical challenges in it. Okay, so we're going to talk a little bit now about the proverbial dead elements. And again, any of you that have worked in ultrasound or are working in ultrasound and had to deal with probes, I'm sure you've heard the term. I've got dead elements, I've got dropout, weak elements, etc. So we're just going to touch base on those a little bit and kind of hopefully give you a little clearer understanding of what those actually mean. Again, and that, in this case, I'm going to be speaking specifically more about PZT arrays with the individual elements. When you have a true dead element, then you have one that is completely broken or cracked in some case. Again, this is a representation of an individual element, and you can see this one's got a crack through it. Keep in mind there's going to be a wire connected here, hypothetically, all the way through the system to fire and receive signals from this element. Once these are dead, obviously applying power to them does nothing. The crystal can't vibrate, the element can't vibrate and generate sound. Obviously, if it can't generate sound, it can't receive sound, so it truly is dead. The one thing about individual element arrays like PZTs is you can see these many times in the image, or at least suspect that you see them. And then as I talk about testing devices and so on, in a moment, you'll see the ways to really look and identify whether you have that. Now, basically, in this case, the element's either going to work or it doesn't. There's no real in-between on these, so it's kind of dead or not. Okay, I got a question here that's come through from Lucio. Can crystal-based transducers produce 3D images or only the capacitive or the CMUT? No. That's a great question. Today, most of your 3D, 4D probes are the composite array type of transducers. CMUT can do 3D, 4D. And I'm taxing my brain here. I would say at this point, and I could be wrong, and if someone knows it, please speak up, but I do not believe there are any single crystal arrays that are produce 3D images right now. But your standard composites are the bulk of your 3D, 4D arrays. Okay, I got another question here from George. Can we say that CMUT is better for abdominal probes? I would say, other than, as I mentioned, some of the sonographers' concerns, the clinical people's concerns about image detail or loss of detail because of the smoother imaging appearance and so on, I think that they would work well there. Now, one of the things that is true, and is you saw my images there on the CMUT were all vascular, so we're talking 4, 5, 6 centimeters in depth. There's still some issues there making sure that with CMUT you can get the penetration required to do good abdominal imaging. But yes, it's certainly from a aesthetic appearance, which I know most radiologists want to see a little bit smoother image in the abdomen. It's certainly a good product. Okay, we have a question from Wayne. Once the crystal is cracked, can it be repaired? The answer to that is absolutely not. You cannot repair this element, and that's a great question, Wayne. There's absolutely no way to repair this. Keep in mind, if you go back to the beginning of my presentation, I kind of showed you how these are made and formed. Once it's cracked, it's dead. There is no repairing a dead element within an array stack. Even from a cost standpoint, it would be incredibly costly to try to do that. You basically have to take apart the array, so you might as well put a new array in it. Great question. Now, again, we've all dealt with and deal with dead elements, but there's a real clinical effect of dead elements, and I think sometimes we all tend to maybe minimize those or not look at them as we should. And I think I've got some examples here that show what really happens with dead elements. Now, one of the things that I typically will say, and I've seen white papers and working with folks, a company like Axess, who's one of our partner companies, who are just experts in probe engineering, that have a lot of information as well on how dead elements affect the clinical performance of a probe. And one of the areas that is you'll really see a clinical effect in a negative way is in Doppler. Again, I make no bones about it. If you take a curved abdominal probe with 192 elements in a composite array, so you've got 192 individual elements, you have 2 or 3, even 4 that are dead, that are out on the outer edges, you're really not going to see very much of an effect in the clinical performance of that, looking at the liver or kidney or something. However, in Doppler, it's a different story. If you look here on the left, we've got a complete array. Now, again, this is a vascular image in this first case here. But we've got a normal pulse Doppler wave, looks as it should, healthy patient. Over here, they've taken the same probe, removed 2 elements to simulate two dead elements, and you can see the difference in the Doppler performance. Now, in this case, any of you that understand the clinical effects, this person looks like we've got some turbulation somewhere in their carotid artery. This person very well could have to go have a angiogram, or even worse case, an endarterectomy to cut them open. And that's not a good thing. That's a physician, a vascular surgeon, a radiologist looking at that, cardiologist is going to say, ooh, we have a problem here. So it's going to require further tests, further inconvenience and pain to the patient, cost, etc. Now here, we're looking down in the abdomen. Again, we've got a normal Doppler flow. Over here, we've got 6 dead elements simulated in this same probe, and once again, we've got a lot of turbulence. Here, where you've got a good clear window in the Doppler spectrum, this shows that, again, we've got some turbulence, some blockage possibly. So I would encourage you to say this at this stage, that when you think you have dead elements in a probe, but you're not really seeing anything in just the 2D imaging, you really need to check Doppler, because Doppler will bring these to the forefront as to whether or not you're being able to provide a true, good, positive clinical performance of that probe. Okay, we've got one question here. Can dead elements, this is from Chandra, can dead elements individually be repaired? Again, no, that's impossible. It's too costly to do if you could do it, because you basically have to destroy the array stack in order to go in there and put an individual element in. So it's far better to just go ahead and replace the entire array stack. Okay, we've got another question here from Logan. What is the difference between a weak and a dead element? If elements are binary, how can they be weak? Okay, this is a great question. In many cases, an element is not necessarily weak. That typically leads me to look at the wiring to that element, as to whether that's making good contact. You can really get crazy and go down and look into the system side and see if you've got a channel out in the system where you're not, again, providing the transmit, receive pulse properly to the probe. So that is a great question, but that's typically where the weak element is. Once an element's going to work or not and go bad or stay good. Okay, we've got a question from Valentine. Will any crack on the probe definitely cause it to be dead? Well, if I understand the question, it maybe if you're talking about dropping it or something like that, it can. Make sure I'm answering your question properly here. Yeah, I mean, if we see a lot of probes that come into our facility where you can definitely see it was dropped because a series of elements will be out; they'll be dead. It's almost as if you take a block and then just cut a chunk of it out. We can see that with some of the test equipment we have. Doesn't mean that every time you drop one that it's going to crack and cause a problem. So it's just a matter of having it tested if you have something like that happen. If the element cracks, now I'll answer that if I misanswered your question. If the element is cracked, it's dead. There's no repairing it. Okay, got another question from Chandra. How do you identify the cable issues to the dead elements? Great question. And if I may, I'm going to touch base on that here in a few slides, but it comes down to being able to properly test the probe. At the level of clinical engineering or looking at that at the site, you can't. I'll just tell you, you really can't. But through proper evaluation of the probe, that you can. And I'll share that with you here in a minute. I'll keep your question here. Again, just some more effects, the dead elements, this one in color, and again, you remember it's colored Doppler. So to the left, we simulated a dead element, and again, there's an effect in this colored Doppler. Now, this is being done on a phantom, but if you were looking at this on a patient, and again, if you're the reading physician, you might suspect some sort of blockage because you're not seeing color through here, so you might be thinking that there's some plaque buildup or something in this artery, etc. Well, over here's what it looks like in a normal, good probe with all elements firing. Okay, we've got a question from George. If you have dead elements on the far sides of the probe, would this still affect Doppler performance? Great question. In a linear vascular probe, and it depends on how many elements, if you've got more than 4, yes, it'll affect it. On an abdominal probe, if you have even 4 and say there's 2 on one side, 2 on the other, no, you're really not going to see a big difference there. Where you will see big problems in dead elements with Doppler, and there's a white paper out that was done, I believe, on a study in Sweden with ultrasound, is in cardiac phased array probes. And if you have 2 or more elements, adjacent elements dead in that, in Doppler, it will give the indication that the patient has mitral regurgitation, which, if you guys know anything about the heart, that is a terrible thing, and that if a cardiologist sees that and didn't know any better, could certainly lead to unnecessary surgeries and further tests. So there's a good white paper out about that. Okay, testing modern probes. I live by this, and I hope all of you do as well. Obviously, if you can't test something properly, I don't know how you can possibly repair it properly and say that you did a good job on it. So you've got to know how it works, how to test it correctly, and then you can obviously offer a repair that is done properly as well, in my opinion. You know, some of the test equipment out there now, the first call over here, and hopefully some of you are very familiar with this. We have several of these ourselves. We use these religiously. This is probably the best device that I know of in the world to truly accurately test probes, and it gives you a nice test electrically, acoustically, etc. The question about the cable, I can probably answer that for you right now. This is a device. Using this device, is one way, again, the best way in my humble opinion, to identify whether it's the cable or the element. And what we can tell by this, just to share that with Chandra, is that a dead element is going to look one way on this test. We can see if there's a bad cable. Basically, the reading we get is going to look different. We can see that the cable is open, broken, etc., but yet the array is still performing. We still got a beam profile on the array. So that's how we can tell with that. Leakage testing, obviously, and again, I hope you're doing that, especially on transesophageal probes. Live testing and the proverbial tissue phantom is also a good way to test probes for a baseline. One of the new devices out by Axess is called the Arion. This device is rather unique, I think, now in the industry. The fact that, unlike the first call, you don't need a lot of adapters and things for each probe. You basically can test any type of probe on this device just using the machine. And I'm going to show you an image on this device. This is a great example. This is a transesophageal probe, a 2D transesophageal probe. What the Arion does a really nice job of is helping you identify whether you're getting any kind of acoustic power to the array. In other words, is the array working? If you look here on the left, here's a picture showing nice bright array. This is a good array, so you can tell even from here that they're getting full electrical power and acoustic power to the array. And then through this beam profile here, you can see that it is firing properly and all elements are working. Here's the same probe with some simulating a bad array, and you can see the difference. The intensity has certainly dropped off, and when you look at the beam profile, you can see that your power to the array is definitely diminished. Now there would be, we have to take that a bit further to see where the problem lies, but your initial response might be that this array is certainly bad. But this is a great device in the fact that with the Arion you can test single crystal arrays, composite arrays. It doesn't matter. It tests them all because it's looking at the acoustic power to the array. So it's really, whereas the first call is somewhat limited as to how many elements it can test, the Arion doesn't care. It can test it regardless of the number of elements. Really unique tool out on the market right now. Okay, we've got a question from Chuck. What would the approximate cost of the test device be? If you're referring to the Arion or the first call. Chuck, if you can maybe ask that, I can give you a ballpark. I mean, they're a little bit different in price, so maybe if you could just clarify that, we can come back to that. Okay, just to move on, I want to talk a little bit about single crystal testing. One of the big probes on the market, it's been out for a few years, and it's an excellent clinical probe, is the Philips C5-1 curved array. That is a single crystal array probe. I think Philips, again, if you looked at it from an individual element standpoint, it's about 6,000 elements, 6,500. Now, I'm showing you a real-world case of a probe that we received in where the customer thought that they had weak or dead elements. And this was done through an air scan, which some of you may do. And, you put no gel on the probe, just turn it on in a 2D mode and look at it. So you can see a little bit here, hopefully it's coming through, that they thought they had some dead or weak elements. Well, before we go further, okay, George, does the Arion also test cable breaks? No, not specifically. But again, what the Arion will do is certainly tell you, hey, we've got a problem here in the array. It's a real problem. There's no power getting to the array perhaps, or the array itself is dead. But there's further testing has to be done to verify the cable. Oh, cost of both? Okay. Well, and this is from Chuck on the cost of the test equipment. And I'll go back here a minute. So the Arion, the first call. I'm not going to speak too far out of line because our partners at Axess sell these devices. The Arion, I believe, is in the low mid-50s, something like that. And the first call, I'm not sure, but we can try to get you that answer, Chuck. And I can certainly put you in contact with Axess on that. Okay, on the C51 then, again, here's the air scan, so you can see they thought they had a problem. Now what we did is when we got the probe in, we were able to actually run a first call with this probe and run it through our testing. Now, one of the things you have to understand about this probe in particular is the C51 was developed by Philips to actually do abdominal scanning on obese patients, frankly. They were looking at a way to be able to get clear, precise, clean images on people that had some obesity. And one of the things they did in the development of this, again, using the single crystal technology, these probes have a very strong acoustic output. They've done some other things, which I'm going to show you on lensing and so on, but it actually performs extremely well. So from a sonographer standpoint, they can, on a thin patient or a heavy patient, they're getting good clinical images regardless using this probe. But because that acoustic output's a little bit stronger than most of your composite arrays, air scans, and this is where I'm going with testing, some of the testing methodologies that we've all used in the past just don't hold water any longer. Definitely on this probe, air scans, and we see it, will lead you down the wrong path. And I just put this statement in here, and again, do with it as you will, but I firmly believe it that, not only proper testing is no longer needed, it's absolutely required. Because in this case, as you can see, we ran our first call, and not to get too technical, but these zones here, in a matrix array, you're firing the arrays by zones, again, because the whole array fires. This thing has a little bit of better backing material, and so it's basically running a little hotter. But after going through the full testing and so on, it's working normally. So we were able to actually test and evaluate it and not have the customer spend thousands of dollars in a exchange or even thousands of dollars in an unneeded repair. So again, by properly testing it, we were able to save the customer significant money. Okay, repair types. Again, I said we go through major and minor repairs, kind of what those mean, if you're not familiar. Major repairs, and this is kind of an industry standard. We're talking about the array replacement, replacement of the entire cable. Sometimes some of you that are having probes repaired now may have run across a cable retermination, which is essentially rewiring the array. Electronic repairs, and most TEs fall into that major area. And these are some shots I want to share with you of some of our replacement arrays, and just so you can see how they're manufactured and made. There's a transesophageal array here as well. I mentioned reterminations. Here's the wiring diagram. It's a very tedious task. A retermination, essentially, what happens is the individual tiny coax wires that attach to the array itself will break, they'll fray, they'll lose contact. So what we do is we have to go in and cut them back, reterminate them to the array. And again, you're talking about, excuse me, anywhere from 64 individual coax wires on a transesophageal probe to maybe 256 on a multiplexed linear probe. So it is a tedious task. Cable replacements on major repairs, just again, just sharing, this would be an entire replacement and what those look like. Terminating the array, I mentioned that. If you look at this, most of the arrays have some sort of flex circuit, and then we have to solder these individual coax wires on here. And these do run from about a 40 gauge upwards to even 48 gauge wire. So it's tiny, tiny wires with a center conductor and a ground shield and an outer jacket. So it's not something that you can just whip out your trusty soldering iron and do. So share some close-ups of that. Again, I mentioned electronic repairs. So many of the probes now are multiplexed, again, where they're using electronic controls to fire the array in different sequences in order to, again, just generate better image quality. Almost all single crystal and matrix arrays are multiplexed. Okay, we got a question from Wayne. What does the FDA say about replacing arrays? The FDA, they don't regulate the replacement arrays. However, it is a very good idea. And let me back up. I'll say it. The FDA does say that the replacement array cannot, the acoustic power cannot exceed that of the original equipment manufacturer, and it must be within a certain range of what the original equipment manufacturer's array's performance is from an acoustic power standpoint. You know, we work again. We work with our friends at Acetera here, who are an FDA acoustic lab themselves, and we do the acoustic power testing here, and then they perform the reading. So we make sure that any replacement arrays we use do not exceed those limits. That's where the FDA will get a little bit, they'll frown on that, and there could be some problems on that. You've got to make sure that the replacement array is performing as close to the original equipment manufacturer's array as possible. For us, a good example was the Philips C51 array. We have replacement arrays for those. When we power tested those, we found out that they were just under the Philips acoustic power, which was perfect. And we found they had a little bit better sensitivity than the Philips array, though they didn't have the full acoustic power. It was close enough that the overall performance is very, very good, but we weren't violating any FDA issues. Great question. Okay, I got a question from Brian. Is it cost effective for a hospital's internal biomed department to have a probe tester such as Arion? Wonderful question. I would say it is completely based on how many probes you have in your facility. And again, I think most folks, including our Acetera who manufactures the product, would tell you this. If you've got 100 or 200 probes or so, yeah, it's a great idea. It can save you a lot of money by identifying problems that maybe would fall into the minor repair category, which is a lot less, obviously, from a repair standpoint. You can baseline incoming probes when your hospital buys new equipment. If you have one of these, you can go in and test the probes when they come in with the manufacturer. And then what you will find is probably 20% of the brand new probes you get have some sort of issue, and you can turn right around and tell the OEM you want them replaced immediately. And that's a fact. They do indeed, I've seen it with my own eyes many times, send you a brand new probe with a brand new machine, and if you thoroughly test it with some of these test devices, it will be bad. But yeah, Brian, it's really dependent on your installed base of probes. If you've got enough, again, I'd say 100 or above, you'll pay for this. You'll pay for this in no time. Okay, we've got one other question. Antonio, do you have experience with probes for ultrafast ultrasound and ultrafast Doppler? If you are referring to the supersonic Imagine, yeah, we're actually working on those. We here at Axess are working directly with Supersonic Imagine, the manufacturer, actually our friends at Acetera are doing some things with them. So that will be coming. That will be coming. Again, minor repairs, strain release, lenses, etc. Housings, connectors. It's that type of thing. The one thing about minor repairs, and this is our historical tracking, they constitute about 80% of all repairs. Certain probes have a higher major repair, maybe an array problem than others, but overall these numbers tend to pan out, and it's what we track to. Obviously, it's the less costly repair. A lot of the minor repairs are due to damage. Here's a strain relief that's gotten pulled. A sonographer pulls the probe out of the probe holder on the side of the machine, and it catches, and they rip it out. Lenses do wear out. Sometimes, though, people will damage them inadvertently. They cut them or drop it, and it damages the lens. A lot of minor repairs you can reduce that within your hospitals by just doing a little preventive training with your clinical people. Okay, we've got a question from George. How easy is it to repair 3D, 4D mechanical probes? Well, it's not easy, George. I will tell you that. I know we here at Axess are getting ready to launch our first model repair here in about 45 days, actually. But that is a unique beast. The 3D, 4D probes are truly electromechanical, so you've got a motor in them. They're oil-filled. There's gears inside, etc., etc. Yeah, they're really not too easy to repair. What we're trying to do is make sure that we can go through and we're using the proper materials and so on to be able to replace like the outer membrane. The oil fill process has to be very good so that you don't get bubbles and things like that in there. There's some internal oil bladders that hold some of the reservoir of oil. So they're not easy to repair. And I know there's a lot of people that try it and they're not real good at it, and there's others that are continuing to work on it. It's certainly something that is in our research and development plan, and we continue to work towards. Oh, okay, we have a question from Chandra. Can one get replacement plastic outer casings cut open for repairs? Not sure I understand that. Oh, well, if you want the outer, if you're talking about the outer housings here, depending on the model, we have several of those. So yeah, we can sell you the housing. It's a little difficult to get those apart, but we could probably talk to you about that maybe offline. I try to get a better idea for what you're asking for. Okay, again, just kind of sticking with how some of these newer probes and so on are really a different breed and a pain for all of us in trying to determine what's wrong. And I'm going to stick on the C5-1 for a minute. It's got a very unique lens on it. And again, when I talk lens, this is the membrane or lens piece that touches the patient. But Philips, and again, in its clinical performance, in trying to keep a clean, well-defined image within heavy patients, they've got a lot of power coming out of it, as I said. So they've got a three-part lens. They've got a base silicone layer and top silicone layer, but right in the middle is an ultra-thin layer of aluminum. And the aluminum acts as a filter, and it filters out a lot of the noise and so on in the probe. Now, what we've seen is that these things pop up. They're adhered to the array stack here inside the C5-1. Here's what it kind of looks like an OEM one. But it's critical that if you have to replace this lens, that you do it right. In the next couple slides, I'm going to show you why. This is a C5-1 lens, and doing what's called a time spectrometry test, we're able to see this is what the attenuation looks like, just sending a single ultrasound beam through the lens, reflecting and back. This is what it should look like on the Philips C5-1 lens. Here's one that somebody tried to do the incorrect way. And I'm not going to go into detail, but you can see that it's rather wrong and messed up. The attenuation is way out of kilter. It doesn't follow the same frequency response or attenuation at all. And here's another picture of it. Doing it again, you can see the average attenuation through here and the difference in this sample. So my point here on this probe and showing you this is that even a thing that would be considered a minor repair such as a lens, depending on the probe, if that lens is not replaced with the proper material, the proper way, you dramatically change the clinical performance of this probe. And that's just a no-no in many ways, especially with your end users. Transesophageal probes, touch on those, any of you that work with those. This is easily the single most repaired probe type in the world. High misuse, and I hate to use the word misuse. It's just any of you that work with them, you know, sometimes the clinical folks don't disinfect them right. They don't use bite guards, so you get holes in the insertion tube here. Then they throw it in Sidex, so the Sidex infiltrates into the probe and corrodes and causes all kinds of problems. You know, we have a full TE repair lab, and you know, we replace arrays and cables and rework everything. But you know, the one thing about TEEs, and I'm showing you some of the problems here. Again, bite marks here, you know, corrosion and things up here, scratch marks on the tip. A transesophageal probe will work forever if it's taken properly care of. It won't fail any more than any other probe, but we rarely ever see TE probes that are well taken care of. So by all means, if you're having any problems, especially with these type of things, punctures in the insertion tubes, scratches on the lens and tips, make sure they're using bite guards. And if they're not, then there's got to be a good reason they need to give you as to why not. Okay, why do we do this? Why do we do what we do on probes? Well, obviously the probe's the only part of an ultrasound machine that touches the patient. I kind of look at it, it's the interface between the patient and the machine, patient's anatomical system and the ultrasound system. I like to think of the probe as the data transfer device, and it's like anything. It's like your computer. If you put bad data into something, you're going to get bad data out. The same thing happens with the probe. You know, the system is dependent on the data from the probe. The system essentially is dumb. It's going to process anything that you send it. If that signal is good, it's going to process it the same way it processes a bad signal. So the probe is really the brains. They do make a difference. Hopefully I've been able to show you a little bit of that, that there are some real clinical misdiagnoses that can occur. And obviously it all boils down to making sure our patients are well taken care of. Kind of just a little bit about probes in the U.S. alone. You know, by estimation, there's upwards of 600,000 probes in service in the U.S. alone. Excuse me. On average, what we find historically is less than 25% of those are tested and or repaired regularly. And I mean tested in a very proper way. They continue to constitute the highest failure item on any ultrasound system is the probe. And those of you doing ultrasound service and support, I'm sure you know that. Repair is still really your best way to go. It's the lowest cost alternative to replacement. I personally think there's some ways that make repairing the probe even better. You know, one of the things that if a company repairs a probe for you and you're sending your probe into them, well, you know the history of that probe. You know when it was purchased. you know the environment it's in, you know how it's used, how it's taken care of or not taken care of. You can even track down how many scans have been performed on that, et cetera, et cetera. Right now, and there's been some people, us included, who tried to look to see if there's a way to determine the history of a probe. Well, you can tell when a probe was manufactured, but there's no way if you get a replacement probe, even from the OEM, that you know the history on that. You don't know where that's been, you don't know how it's been taken care of, how it's been used, etc. The gentleman asked about the test devices. Again, if you have a probe inventory that's significant, a lot of ultrasound machines and probes, you know, get an REON, get a first call, and test and baseline your probe inventory. You know, test it at least once a year, if not a couple times a year. In some cases, when possible, test your probes on each PM. At the very least, when you're doing a PM, make sure you look at all the probes on the machine. And what we do is important, obviously. You know, there's a 3D image, so there's a little baby that's behind that, so we got to make sure that those images are proper and don't show something wrong that is not wrong. Just a little statement from Dr. Powis. Effective probes are in use every day across the United States, delivering suboptimal studies. This statement right here, the attitude remains that ultrasound either runs or it doesn't. If it doesn't, call the OEM, is certainly not accurate. You can have a degradation in ultrasound or problems, as I hope I've shown, that are causing you clinical issues. So it's not just a matter of it breaks or it doesn't. So we've got to be on top of that by testing and looking after our probes. Is it important? Well, of course it is. I think, you know, when you're looking at repairing or exchanging probes, make sure that you ask yourself a few questions. You know, do you want that probe used on yourself or a family member? That's something we use here all the time, especially on when our probes go out. That question is asked. You know, ISO certification. I'm a big proponent. Make sure that you're certified. Your companies you're using are certified in 13485 device probe repair specifically. And the big one is, how are your suppliers testing and measuring the performance of the probes you send them, because it truly does matter. We mentioned acoustic power testing, something we do. This is one I believe in firmly. This bullet point 3. You know, if the probe's not working at 100%, can we really expect that patient exam to be 100%? And I think the answer is no. We can't. And it's all about the patient's life and well-being. I unfortunately have seen an individual, one that pops in mind, who actually had his carotid arteries opened up because they thought they saw something, only to find out that they had a bad probe. And that's not something that any of us want to go through. It's unnecessary surgery. Again, what's this mean for you as engineers? Probes are becoming more complex, and they're going to continue to get more complex. There's no question about that. You know, the testing is a big thing, being able to properly identify what's going on. Again, what used to look like dead elements on a PZT array, well, now in single crystal, it can be electronic issues. Again, you can see multiplexing issues, maybe a depolarized array, etc. As you well know, probes are costly if you have to replace them. A huge proponent of this, we do a lot of it actually for customers, is we'll come in and just train a department. Here's how you clean and disinfect and handle a transesophageal probe. Here's how you handle your intercavity probes, etc. Catching them early. You know, I would much rather have a customer pay a few $100s for a lens replacement rather than let that lens fully delaminate, fluid get in there, and destroy the array, and now you're talking a few $1,000s. The clinical outcome, again, is huge. And, you know, one of the things that, rest assured, there's a lot of us out there that are continuing to develop repair capabilities and so on to help drive cost out on the probe repair side. And The new probes are certainly in our plan and others, and they have to be so that we can handle these technological changes from the OEMs. Well, again, I want to thank all of you for attending. I want to thank TechNation again for this opportunity. There's my email and phone numbers. Anytime, I'll be happy to answer any questions or help you with anything that I possibly can. But again, I'll just open it up for any questions and answers at this time.